So, welcome everybody. Today, Nick Jamesson, grad student of CU Boulder, is going to talk about solving promised systems of equations over finite algebras. Please, Nick.
Thank you, Peter. As he said, I'll talk about solving promised systems of equations over finite algebras. So what is that? To define what that is, I'm going to need to talk about what a promise constraint satisfaction problem is. So I'll just briefly talk about what a constraint satisfaction problem is first, so that we understand. So a constraint satisfaction problem will involve a relational structure. For example, a graph here that I have, a complete graph on 3 vertices is an example of a relational structure, the domain being the set 1, 2, 3. The edge relation will contain all these pairs. And CSP-A, where A is a relational structure, is a computational problem in which the input is going to be just a list of constraints in the signature of A. And the problem is there an assignment of the variables to elements of A such that each constraint holds? So can you plug in the values from the domain of A such that when you plug in those values, for instance, in this case, X, X, Y, whatever you get is that actual tuple of R1 in A here. Okay, so that's a constraint satisfaction problem. And in the previous example that I've given, this can be interpreted as is a given input graph 3 colorable, CSP K3, where K3 is the complete graph on 3 vertices. Okay, so this is a constraint satisfaction problem. And then promise constraint satisfaction problems, the setup is similar, but we now have 2 relational structures, A and B, both in the same signature, with a homomorphism from A to B. So this is like a technical condition that's required for this setup to make sense. And the input is going to look exactly the same. It's just going to be a list of constraints in the signature of A and B. So it'll look exactly like the input in a CSP. But now the problem is there an assignment of variables to elements of A such that all of these constraints hold, or is there not even one in B? So you can think of B as like a larger structure in which it's easier to satisfy all these constraints. Going back to the previous example with the complete graph on 3 vertices, you can set up a promise constraint satisfaction problem by looking at the complete graph on 5 vertices. So there is a homomorphism from K3 into K5. It'll just embed into there. So this makes sense. And the interpretation of this problem is now, is a given input graph 3 colorable or not even 5 colorable? Okay. Okay. So this is called a promise constraint satisfaction problem because the input instances are promised to satisfy the either A has a solution, or sorry, there's a solution in A, which is called the yes instance, or there is no solution in B. So you can't have a solution in B with no solution in A. So every instance will satisfy that it's either a yes instance or a no instance. That's the promise. And then this homomorphism that I mentioned kind of makes the problem make sense. So you can't have an instance which is both a yes instance and a no instance. So if you have a solution to a list of constraints in A, you apply the homomorphism that exists here, you get a solution to that list of constraints in B. Okay. All right, so then what I'm interested in, what I'm going to be talking about mostly, is promise systems of equations. So the setup is similar, but now we're working with algebras instead of relational structures. So I just have bold A, bold B written out here, finite signatures. Again, you have this homomorphism from A to B in the setup. Now your inputs are just systems of equations in the signature of A and B. And the question is there a solution to the system of equations in A or not even a solution in B? So very similar setup to the PCSP. This is a relatively new topic. So this paper by Larari and Givney in 2024 looked at promise systems of equations over semigroups, in particular They got a result for monoids in terms of looking at the computational complexity of this problem. Yeah, and so the goal of this talk is to kind of generalize some of the results, talk about generalizations of some of the results that they have. Yeah, and so I've mentioned PCSPs and promise systems of equations. The two are related. If you have a promise system of equations, you can kind of convert it back to a PCSP by instead of looking at a system of equations, you look at the graphs of the functions, and you can kind of write out a system of equations as a list of constraints instead. So that's what this theorem says here. LaRose and Zadori, 2006. This is just a theorem about the CSP case, but there's nothing that changes in the proof for the PCSP case. So you have a promise system of equations, just look at the graph relations of the functions, and you can view it as a PCSP. So this is nice because there's a lot of theory about PCSPs that you use to prove, in particular, to prove like NP hardness of a particular PCSP. So being able to view a promise system of equations as a PCSP is very useful. Okay, so our problem is, what is the computational complexity of promise equations A, B? So throughout here, I'm going to be just working with finite structures with finite signatures. So meaning you can always do everything. You can always look for a solution with brute force. We'll also just work under the assumption that P is not equal to NP. So some known results. So the famous CSP dichotomy theorem for finite will apply to finite algebras here. And this will tell you the computational complexity of systerm A, which is actually just the same thing as promise equations AA, is going to be either P or is NP complete. Okay, so the goal is to kind of get similar dichotomies for the promise equation case. For now, it's known, all known examples are either NP or NP hard, the ones that we know about. So for the tractability part, you can kind of appeal to the previous theory on CSPs or systems of term equations to get tractability for a promise system of equations. And that the way you do that is this, what's called a sandwich. So if you have some C, such that A maps homomorphically into C maps homomorphically into B, then promise equations A, B will reduce to systerm C. And this previous bullet point up here that settles the question on complexity of systerm C tells you some information about that. So you can always get tractability results if you have this sandwich here. Yeah, so notice if you have a yes instance of promise equations A, B, that means there's a solution to a system of equations in A. You apply your homomorphism, you get a solution in C. If you have a no instance of promise equations A, B, that tells you there's no solution in B, which means there couldn't have been a solution in C because you would be able to apply the homomorphism and get a solution in B. So that's the reduction there. Just you use the same instance. Okay. For hardness of a promise system of equations, you need to look at the set of polymorphisms from an algebra A to an algebra B. You need to look at how rich that is. Okay, so polymorphisms, probably you're used to seeing polymorphisms from a power of A to itself. The more general definition is you just have two algebras, A and B. The polymorphism is going to be exactly what you would expect, just a homomorphism from a power of A into B. So some facts about polymorphisms are that the polymorphisms from A to A are going to determine the complexity of systerm A. Again, that's promise equations AA. Wanted to state it in the promise equation language. Sorry. Pol AB, set of polymorphisms from A to B, will determine the complexity of promise equations AB. More precisely, you have this statement here. If Pol AB is contained in Pol A prime B prime, where everything had, so A and A prime are going to have the same finite domain, B and B prime also have the same finite domain, then PCSP. Okay, maybe I should have written promise equations, A prime, B prime, reducible to promise equations, A, B. The same holds for relational structures and the language that I have here. So the idea here is that you can think of let's see here. Yeah, so you can think of A prime, B prime as having kind of like fewer operations than Pol AB. So when you throw in more operations, say you just expand A prime and B prime and you get AB, you throw in more operations, it makes it harder to solve a system of equations. And you also get fewer polymorphisms. The more operations you have, the harder it is for a function to compute with all those operations. So that's like the intuition behind this statement in number 3 here. Okay, so we're interested in looking at a set of polymorphisms from one algebra to another in analyzing the complexity of these problems. Okay, so Pol AB, it's going to act a little bit differently than Pol AA, which is a clone, but we still will have some structure on Pol AB. So in particular, it's going to be what is called a minion. To define a minion, I'm just going to define a minor of a function first. So a minor, so this definition basically just says f superscript pi here is a minor of f if you can obtain it from moving variables around, identifying some variables, or introducing some dummy variables. That's a minor of f. Okay, and a function, a set of functions from powers of A into B, which is closed under taking minors, is going to be called a minion. If you have a polymorphism from A to B, and you just identify variables, move variables around, introduce dummy variables, you'll still have another polymorphism from A to B. So Pol AB is a minion. Okay. As I said, we want to analyze Pol AB in order to determine the complexity of promise equations AB. So there's this paper, Bartow et al., algebraic approach to promise constraint satisfaction, which lays out a lot of theory for analyzing Pol AB. There's a lot of hardness conditions used. There's a lot of hardness conditions in that paper that you use to prove hardness for a PCSP. Okay, so, oops, okay, this is a typo. The slides have shifted around. There were no previously stated dichotomy results. Upcoming dichotomy results will use the following. Okay, so if you have a minion and you have a constant k, this function here, I, will take polymorphisms from that minion and it will select coordinates from that polymorphism. So P is an n-ary polymorphism here. I will take some subset of the arity n. And if I satisfies that it's bounded, and this technical condition involving minors, then I will be called a selection function. So this technical condition basically just means I plays nice with taking minors. So this is what I'll call a selection function for M with bound K. And as I mentioned in this paper, this is a nice tool for proving hardness because if you have relational structures with a homomorphism from A to B, so you have the PCSP setup, and you have a selection function with bound K for this M, Paul A, B, then PCSP is NP hard. So if I go back to the previous slide, maybe the easiest example is let A equal B, and suppose you have Paul A, B is just the set of projections. So then if I go back to this slide, your selection function that you would take here would just select whatever. So if your projection function is P sub I, your capital I will select little I there, and that will be a selection function in this case. With bound, I guess I have strict inequality, so with bound 2. Okay, so if your polymorphism minion is just the projections, you get an NP hard CSP there. Okay, so the first result I'm going to mention involving promised systems of equations. As I mentioned, this started with this paper by Lowry and Gibney in 2024. They looked at complexity of promised equations A, B, where A and B are monoids. And so they have a dichotomy for monoids possibly expanded with additional constant zero area operations. And the criteria is if there exists a nice homomorphism from A to B, such that the image is a commutative monoid, which is a union of subgroups, or a commutative regular monoid, then promised equations AB is NP. Otherwise, promised equations AB is NP hard. So this is kind of the first dichotomy result. And I'm going to talk about kind of generalizing this. Okay, so first, this thing I have here about possibly expanding with additional constants. If you just have two monoids and you don't have additional constants in there, every system of equations is trivially solvable by just plugging in the identity that will solve any system of equations. So this becomes, or in the language of this theorem, there'd be a homomorphism from A into a trivial monoid, which is going to be a commutative and a union of subgroups. So, okay. 2025, they generalized this result. So before they were just expanding monoids with constants. And now this result generalizes that by expanding monoids with just arbitrary relations. So if you have, and A can be finitely generated, not just finite. Okay, so if you have a finitely generated monoid, and then it maps into a finite monoid homomorphically, you expand them with additional relations, they still have a dichotomy for this. I'm kind of using abusive notation here, PCSP, A, RA, B, RB. What I really mean here is convert everything back into the PCSP format where you just look at the graph relations of the functions and consider this PCSP. We don't want to be mixing a system of equations with constraints involving the relations R, A, and RB. And so this is a little bit of an abusive notation, but that's what I mean here. Oh, and that's what I just said there. Okay. So my result here is just a generalization of the result on the previous slide. So A and B are no longer going to be monoids. They're just going to be finite algebras. We're still going to expand them with relations, just arbitrary relations. We'll have the usual homomorphism. And we're going to have a binary polynomial operation with both a left and right identity. Now, instead of just a basic operation as in the monoid. Note that this is, oops, okay. So I still have a dichotomy for the PCSP AB in this case. Note that the operation here is not even necessarily associative. So it's not a basic operation of the algebras, and it's also not necessarily associative. So that's where the generalization is. Oops, sorry. I've not stated the theorem in full detail here. So there's a criteria for when PCSP ARA BRB is in P. We're going to need a little bit more machinery to talk about what that criteria is. Okay. So we're going to be working with a binary polynomial operation instead of just the monoid operation. So in order to do that, we're going to need the following definition. Because in the proof of the result, there's a lot of work involving the polymorphism P in this case, and how that interacts with the binary polynomial operation. In the case where the operation is, again, just a basic operation of the algebra, like in a monoid, that basic operation just commutes with any polymorphism P. But with a polynomial operation, this definition here is useful to make notation a little bit more manageable. So if you have a binary polynomial operation, it's just going to look like this. X dot y is some term operation with C1 through CK constants plugged in, and two variables. And this induced multiplication dot subscript P on the algebra P of a to the n is going to be defined this way. You just apply P to all of the constants here. And this is the definition that's needed to kind of make multiplication play nice with the polymorphisms. So what you get here is that P of a product is going to be the product of the P's of the tuples here. This is the last line. So again, if this is just a basic operation of the algebra, you don't need to do anything. But for a polynomial operation, this dot sub P is useful so that I can just use this last line here repeatedly in any argument where it comes up. The proof is just one line that I guess takes up two lines, but just apply the definition of polymorphism to your binary polynomial operation, and you get this. So it's a trivial lemma, but it's very useful. Okay. Cosets. So if you have a finite commutative monoid, which is a union of subgroups, or a finite commutative regular monoid, the way this is going to look is that every element of this algebra is going to be contained in some maximal subgroup of A. Each of these subgroups will have a unique inverse for this A. And in this case, I want to define this operation here, T by X times Y inverse times Z. So this makes sense if you have these inverses. And if you have a relation on A, I will call the closure of that relation under the operation T here, the coset generated by R. And I'll just use brackets R to denote that. And so now I've assembled all the language that I need in order to talk about the criteria that I have for the promise equation AB to be in P in my theorem on this slide. So there's a criteria here. And now we're ready to actually state it. Okay, so there's a lot. This is very dense, but you have an algebra A and algebra B. I've explicitly written out the operations in these algebras. Dot is a binary operation, binary polynomial operation that comes from all these Fs and potentially plugging in constants. E will be an element of A, which serves as both a left and right identity for this binary polynomial operation. So these algebras, they could be monoids, but this is a more general statement. Again, we'll expand the algebras with arbitrary relations, RA and RB. And then to make the statement of the theorem a little bit easier to parse, I'm just going to kind of assemble all the information of all of the functions and these additional relations into one relation, SA and SB, by taking a Cartesian product. And then you look at, I've just called A with SA and B with SB, A bar and B bar respectively. So these do have all the information of the functions originally in our algebras and the additional relation. As usual in the setup, you have to assume that there's some homomorphism from A bar to B bar to talk about PCSP A bar B bar. And the criteria here for when PCSP A bar B bar is in P is if there is a nice homomorphism psi, so it has to satisfy some conditions. The image of A under this homomorphism with the induced polynomial binary polynomial operation is going to have to be a commutative regular monoid or commutative monoid, which is a union of subgroups. So in the case where these are just monoids, this coincides with just the criteria that the image of A with its basic operation is just a regular commutative monoid. So here the operation changes to this induced polynomial operation. The next condition is that this operation x, y inverse z, but now with the induced polynomial operation being the multiplication, so this t from the previous slide, is a polymorphism of the algebra psi of A. So this operation, x, y inverse z, plays nice with all the operations F1 through FR here in psi of A. And then the last condition is that this operation has to play nice with the additional relation that we've expanded A and B with. So this coset notation that I've explained is used here. So the coset generated by psi of R of A is contained in RB. So these are the conditions that you need for PCSP A bar B bar to be in P. And if you don't have those conditions, then PCSP A bar B bar is NP hard. So I'm more interested in what happens when you just look at algebras as opposed to algebras with expanded with additional relations. But if we go back to the previous slide, notice that if this theorem still holds if you don't expand with RA and RB, you can still collect all the F's into this relation S. Condition 3 just disappears then, and this statement becomes a lot nicer. And so you can do this if you're just working with algebras. And so if you're doing that, can you actually apply this theorem to interesting classes of algebras? And the answer is, of course, yes. So some examples, lattices, mouse of algebras is the big one. That's really the end goal of this talk, is to get to the mouse of algebra case, because the statement there is much nicer. And then, of course, if you have it for mouse of algebras, you get a dichotomy for any algebra, which is a mouse of algebra. Okay, so I mentioned on the previous slide lattices. So if you have two finite lattices, possibly with additional constant zero area operations. So you can think of those as expanding with singleton relations for whatever constant symbols you want. You have the usual homomorphism from one algebra to another. And if you go back to the previous theorem and look at what does this mean when you're just working with lattices, the criteria becomes a lot simpler. If there's a homomorphism such that psi of A is a one element lattice, then promise equations A, B is NP. Otherwise, promise equations A, B is NP hard. This is actually so you'll notice that if we've expanded with additional constants, and by the setup of the problem, there has to be a homomorphism from A to B, that homomorphism is going to preserve constants. And so unless all the constants in B, unless all the constant symbols in B are interpreted as the same element, and that element forms a trivial one element lattice, you will not get this homomorphism that whose image is a one element lattice. So these are usually going to be in the NP hard case. Yeah, so if we look at the previous slide here, again, we can kind of like look at condition 2. And in the case of a lattice, you have to have the operation here, x, y inverse z, which is just going to be obtained from the meet, has to commute with the join. And the only way you're going to get that is if you have a one element lattice. So that's where that's coming from. Okay, so now Malsev algebras. This is the most important case. A Malsev algebra is going to be an algebra with the term M satisfying this identity here for all x, y, and a. mxxy equals m y xx. Okay, classic example of a Malsev algebra is a group. It's pretty easy to see. And then this previous theorem, after a little bit of work, you can get this to work for Malsev algebras. Now notice that if you let E be an element of A, and I put E into the middle component of that Malsev term, M of x, E, y is going to be the desired binary polynomial operation, which has both the left and right inverse. And if you do some further work, the criteria from the previous theorem here, number 2, in the Malsev case, is just going to turn into this criteria that psi of A is abelian. I have not expanded these Malsev algebras with additional arbitrary relations, so condition 3 in that previous theorem is now gone. But if you have a homomorphism from A to B such that psi of A is abelian, promise equations A, B is NP. Otherwise, promise equations A, B is NP hard. Okay, so the easiest case, and this already would follow from the very first paper by Larari and Givny, where A and B are groups. Excuse me. If there's a homomorphism from A to B such that psi of A is an abelian group, then promise equations A, B is NP, otherwise NP hard, exactly what you would expect. For rings, again, you kind of just look at what it means for a Malsev algebra to be abelian. In particular, the Malsev term is going to have to commute with the other operations. The only way that's going to happen in a ring, in the image here, psi of A, is if the multiplication is a zero multiplication. In other words, if you multiply two things together, you have to get 0. So that's the only way you get an abelian ring here. And that will tell you that the promise equations A, B is NP. If you have a homomorphism, psi, such that the image psi of A is an abelian ring. Okay, so I wasn't sure I was going to get to this. I guess I have 15 minutes. I might not get through. I might not get through all of this. But what the next part of the talk is just a little piece of the proof from the original paper by Lorari and Givney. And I want to talk through a little bit about how I can adapt this in the more general case. I have some slides on that at the end. I might not make it to those, so I'll kind of just talk through this as I go. So if we remember back to the slides on selection functions, the way you prove hardness for these things is you want to find a selection function on the polymorphism minion, pol AB, that satisfies those two conditions that I had on the previous slides. One of them was that it was bounded. The other was that it kind of plays nice with minors, this technical condition. So this is the original statement from the 2024 paper, just involving monoids, possibly with additional constants. As I said, we want to prove hardness. So that's the little piece of the proof that I'm going to go over. So if you look at the criterion, this says that if there's a psi for which the image psi of A is commutative and a union of subgroups, then promise equations A, B is NP. Otherwise, it's NP hard. And so we want to assume that there's no such psi and show that we can construct one of these selection functions to get NP hardness. Okay, so first thing to note, if you have a polymorphism from A to B, then if you take P, what I call P delta of X, define it to be P of XXXX, that's going to be a homomorphism from A to B. And in particular, this means that from our assumption, the image P delta of A cannot be a commutative monoid. No such homomorphism exists such that the image psi of A is going to be a commutative monoid, which is also a union of subgroups. Okay. So we'll call M pol AB. And then we want to split up M into disjoint sets. So one of these sets will be the P's such that this P delta of A, this image, is not a commutative monoid. The other will just be its complement. In our setup, M2 is going to be the set of all P where this image P delta of A is a commutative monoid, but it's not a union of subgroups. This just comes from the criteria on the previous page, because any homomorphism is not going to be both satisfied that its image is both a commutative monoid and a union of subgroups. Okay. And we're just going to look at, in this part of the slides, we're just going to look at M1. So we need to construct a selection function for M, but you can kind of do that in pieces. So M1 and M2, you can check that those are actually both still minions. They're closed under taking minors. If you have any two functions, one where one is the minor of the other, then this P delta and Q delta will coincide here if Q is a minor of P. So what you can do is you can define a selection function I1 for M1 and a selection function I2 for M2. If they're both bounded, then you'll get a selection function for M by just taking the max of the bounds. They'll both still play nice with taking minors because they're M1 and M2 are both minions, so those conditions will be satisfied. So when you take the union of the functions, that condition will still be satisfied. Okay, so we want to look at the construction of a selection function for M1. So we're going to look at an arbitrary n-ary polymorphism in M1. In other words, the image, what it means to be in M1 is that the P delta of A, that image is not a commutative monoid. And then I'm going to define another function here. So P is n-ary, and for each I in the first n integers, we'll define Pi by putting the identity in every place except for the ith component. We'll put a variable in the ith component. So that's Pi of x. That's going to still be a homomorphism from A to B. And then we'll define the selection function. We'll select coordinates such that Pi of A is not a commutative monoid. So the idea here is that if P delta of A is not a commutative monoid, then some of the pieces, some of these pieces, Pi of A, have to be non-commutative as well. You can't have all of these pieces being commutative and still get the P delta of A is not commutative. Okay. You need a bound. This is a little bit mysterious, but you're going to just take the number of subalgebras of B, which are not commutative monoids. And then I'm going to claim that I1 is a selection function for M1 with bound K1. And since I had my generalization involved, since I mentioned my generalization already, I want to, let's see. I want to look at this bullet point here, where the selection function is defined. Wait a minute. Yeah, so in the more general case, we're going to be using the binary polynomial operation. So instead of saying Pi of boldface A, I'm going to be looking at Pi of just the set A with that induced binary polynomial operation instead of just Pi of A here. Okay, so some basic results that you need in order to prove that this thing is a selection function. First, take two elements, two indices, and notice that if I and j are different indices, then the elements of Pi of A are going to commute with the elements of Pj of A. So the proof is just a few equations here. First equality is just the definition of Pi, Pj. Then we're using that the multiplication commutes with the polymorphism P, so you can pull the multiplication inside of P. Then you can just pull out Pj of B on the left. Again, multiplication commutes with P, so you can do this. And then this is exactly what you want. So elements of these different components here kind of commute with each other. Okay, so that's the first thing. Okay, so if Pi is commutative, so if all the pieces are commutative, then I claim that the image of P is also a commutative monoid. Okay, so we're just going to write down what that means. You take two arbitrary elements in this image, P of An. Again, multiplication will commute with P because P is a polymorphism. So you can pull multiplication inside of P in this first equality. You can then pull this out piece by piece. There's an identity in A, E. And so I'm just pulling out the first coordinate, then pulling out the second coordinate, multiplying them all together. This works again because multiplication commutes with the polymorphism P. Then by assumption, I have that Pi of A is commutative for each I in the first n integers here. So now I can swap A and B in each component and then just repeat everything again, combine and split apart again. Okay, P delta of A is a subalgebra of P An. Remember, P delta of A is just, or P delta of X is just P of X, 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 etc. So if pi of a is commutative for each I and n, it would tell you that this larger algebra is commutative, which would tell you that p delta of a is commutative. Okay, in the original assumption that we were working with, that is not the case. So it is not the case that each of these pi of a's is a commutative monoid. Some pi of a is non-commutative, and remember that I1 is selecting the coordinates in which pi of a is non-commutative, which is to say that I1 of p is non-empty. So this is getting closer to the non-emptiness condition involving I playing nice with minors. I'll make a comment because I don't think I'm going to get to the last slides where I kind of discuss how to adapt this to the more general case that I have. So I'll just mention that kind of trivial lemma that I had about multiplication with a binary polynomial operation is used in the more general case here. Here I haven't even written down what the multiplication is. In the more general case, you just do some bookkeeping and you have on this leftmost product, you would have dot sub p, an induced binary polynomial operation from the polymorphism p. And on the inside, you have just the regular dot, the binary polynomial operation. Everything still works out nicely. You just have to kind of do some bookkeeping with your operations. Okay, so then I want to see that this non-emptiness condition or this condition about I playing nice with taking minors holds. So we will consider a minor of P. And this condition, if you don't remember it from the previous slides, because it's rather dense notationally, just says that I1 of Q intersect pi of I1 of P or is non-empty. Okay, well, on the previous slides, we've already shown for an arbitrary polymorphism that I of that polymorphism is going to be non-empty. In other words, I1 of Q is non-empty. That's what we've already shown. And so in order to show the second bullet point, in this case, it suffices to show that this I1 of Q is a subset of pi I1 of P. That will give you non-emptiness of the set in the second bullet point. Okay, so let I be an index in I1 of Q. And we want to see that that's in pi I1 of P. Well, what it means for I to be in I1 of Q, well, the selection function is selecting out components such that Qi of A is not a commutative monoid. Yeah. Okay, and then so we're going to kind of rinse and repeat the argument that we've done before. So we're going to let A be a member of the algebra A. We'll just write out what is Qi of A. By definition, it's just A in the ith component, E is everywhere else. And okay, a little bit of abusive notation here, but P of E, AA, E. What this means is because Q is a minor of P, the second line is just E's and A's, and the A's occur in only the coordinates that get mapped to I under this map pi. So the preimage of index little I under this map pi. I can split this second line apart again using the fact that multiplication commutes with the polymorphism P. And now what we have is a product of components. So we're going to kind of rinse and repeat the argument from the previous slides. If the image here, Pj of A, is commutative, for each j in the pre-image of I here, then the image qi of a is also going to be commutative. Again, this is just this. It's going to be the same argument as we did before. If all of the little pieces are commutative, then when you do their product together, that product is also going to give you a commutative monoid. Okay, so then the last thing I'll say. Okay, so the last part just means exactly this, that I1 of Q is indeed a subset of pi I1 of P as desired. Okay, so this gives you the little piece of the selection function. Again, for the more general case, which I think I have, I don't have time to talk about the bound. But for the more general case, again, this idea of just swapping the multiplication with the binary polynomial operation. You just do bookkeeping all the way through using the correct multiplication whenever you pull it inside the polymorphism or outside. So then I believe I'm out of time now. Okay, so I'll just scroll to the end. Okay, so brief discussion on generalizing and then open questions. So there, I've established this dichotomy for promise equations A, B in the case of Malsev algebras. So naturally, the open questions that I want to look at are what about if A and B are in a congruence modular variety, and what if A and B are in a Taylor modular? Okay, so that's a typo. Taylor variety. Okay, some abuse of copy and paste maybe is going on. Okay.
Thank you. Any questions for Nick?